traffic is consistently soaring. Application servers can rely on their powerful scaling capabilities and a human wave tactic to cope with high loads. Yet relational databases often find themselves in a quandary, unable to easily scale, becoming the bottleneck of the system. Today, we first explore the simplest feasible solution: read-write splitting. Read-write splitting involves the primary database real-time replicating changes to secondary databases, ensuring that these secondaries also hold complete replicas of operational data. By distributing data access traffic across the primary and secondary databases, the pressure on a single database is alleviated. Here, the primary handles both reads and writes, while secondaries are dedicated to read operations. Thus, implementing read-write splitting entails two crucial steps: 1. Replication, and 2. Traffic distribution, which equates to database load balancing. A common approach involves introducing an intermediary layer of proxies, which, based on predefined rules, direct traffic to suitable database nodes. This makes the database cluster transparent to the business, with applications interacting as if with a solitary database. Meanwhile, don't overlook the high availability design of the proxy itself to avoid inadvertently introducing new risk points while enhancing database stability. Traffic distribution can also be implemented at the application code level via direct client connections, offering extensive customization possibilities. But this flexibility necessitates that every SQL request decides whether to hit the primary or secondary, and in scenarios of database master-slave switching or fault migration, each client must be aware and adapt accordingly. To simplify this process and ensure consistency, leveraging Zookeeper for unified configuration management is common practice. Having covered load balancing, let's turn to master-slave replication. When the master database executes an update, it first modifies data pages in memory, logs the redo log, writes to the binary log, and finally commits the transaction. Following this, the client can be notified of the task's completion. However, if data is to be replicated to the slave database, the binlog, nestled within the two-phase commit process, becomes instrumental. The binlog is a logical log, akin to a surveillance camera, comprehensively documenting every action taken by the database. It records information in two ways: first, by preserving the SQL statements themselves, and second, by saving the before and after states of the data. Should you inadvertently delete a database, resist the urge to panic. Restoration to a point before the mishap can be attempted using the binlog. Leveraging the same principle, the master's binlog can be streamed in real time to the slave to facilitate synchronization. Once synchronization is initiated, a dump thread fetches the latest binlog entries, forwarding them via a persistent connection to the slave. There, the slave's I/O thread records these entries into the relay log, which acts as a buffer to synchronize the speeds of the two databases. The SQL thread then retrieves logs from the relay log and replays them on the slave, ensuring the slave's data mirrors that of the master. However, there is latency involved in the transmission of bin logs. This means that operations performed on the primary database will not be reflected on the secondary database for a certain period. For instance, a user who has just placed an order might be puzzled when they cannot find it due to the replication delay on the secondary database. To tackle this issue, the most common approach is to circumvent the problem at its core. In some scenarios, read operations can be forced to execute on the primary database. For example, if a user wants to check an order they've just placed, they would do so on the primary database. Meanwhile, the merchant, who typically can tolerate a slight delay, would query the secondary database. Under normal circumstances, a merchant receiving an order a few seconds later poses no significant issue. Additionally, the business process can be designed to intentionally introduce a brief delay. After placing an order, for example, a confirmation page could be displayed for 1 to 2 seconds before redirecting to the order list. This strategy buys extra time for the secondary database to synchronize, thereby reducing the likelihood of inconsistencies being noticed by the users. Moreover, introducing a caching layer on top of the database is also a viable option. When writing to the database, simultaneously write to the cache, enabling quick retrieval of the same data from the cache if it is needed again in the short term. Through these three methods, most practical issues should be addressed, but there are times when we desire greater precision. We can also monitor the synchronization latency of MySQL, and subsequently utilize code to dynamically select which database to use, or wait until the replication lag on the slave is below a certain threshold before initiating queries. Executing show slave status on the slave server returns a parameter, seconds behind master, indicating the delay in seconds between the master and slave. If there is no delay, it returns 0. However, even if the lag is less than 1 second, which could encompass thousands of transactions, it still returns 0. Therefore, for greater precision, we can confirm whether all received logs on the slave have been fully synchronized by comparing whether these 4 points related to the binlog positions are consistent. If GTID synchronization is employed, we can further enumerate the details of transactions awaiting synchronization by examining the inclusion relationship between these two sets. The aforementioned solution appears flawless, but is fraught with issues. Firstly, is this method truly accurate for assessing replication lag? Revisiting the show slave status command, its measure of delay considers logs already received by the slave, the relay logs. For instance, a transaction named TX4, which has already entered the relay log but has not yet been replayed, would be correctly identified as being in a delayed state. However, if the log sent from the primary database hasn't been received by the secondary database, it won't be accounted for in the metrics provided by the show slave status command. This is the case for TX5, which is still in transit. In standard asynchronous replication, once updates are dispatched to slaves, the master commits transactions without awaiting confirmation of synchronization progress, potentially resulting in the master committing transactions unknown to the slave. Switching to semi-synchronous replication mitigates this, where the master awaits acknowledgement from at least one slave before committing. Yet, this compromise does not guarantee that the queried slave is the one that confirmed, leaving room for inconsistency. What if there's persistent lag between the master and slave? Under low write volume, the master completes writes and replicates to the slave, achieving harmony. But under moderate write pressure, the master consistently outpaces the slave, which perpetually plays catch-up. If reads depend on absolute master-slave consistency, the slave seldom gets an opportunity to serve queries. To genuinely resolve these issues, alternative strategies are required. In most scenarios, absolute consistency between master and slave is not crucial. Instead, it's about verifying if a recent update on the master has been reflected on the slave. After updating the master, promptly execute show master status to capture the latest transaction position in the binlog. Pass this information to a verification function on the slave to ascertain if all preceding logs have been read and applied. Once the change is confirmed effective on the slave, reads from it are deemed safe. That's it for this episode. Drac Inner here. Subscribe and see you next time.